guys try the graphing, because remember, nothing has changed. We're still stretching, compressing, all the same rules as before, but starting with a new shape. This shape might annoy you the most because it might not be what you're used to looking at. Okay? So the greatest integer function, the parent function, so you can just put this on your green door. The greatest integer function is not on your note guide, so just on the green door right here. So you write the title, greatest integer function. Then you write the equation of the parent function. So the parent function equation is y equals, and then it has like these brackets around x. So in order to use these properly, we have to have some understanding of what these brackets mean. So the reason it's called the greatest integer function is it takes whatever number you put in the brackets and it rounds it to the greatest integer that is not larger than the number you were given. So let me say that again. It rounds it to the greatest integer that is not bigger than the number you were given. So you can't exceed the number that's sitting inside the brackets. Okay? So for example, if somebody put 1.2 inside the brackets and you calculated it, what would it turn 1.2 into? Check. 1. Good. The greatest integer it can reach without going past 1.2. So integers would be 0, 1, 2. So it can go up to 1, but it can't go up to 2 because 2 would be past the number that's in the brackets. Okay? So this would get rounded to 1. What if it was like 1.999? See? 1. Okay? Doesn't matter how close it is to 2. If 2 is past it, you can't use 2. Okay? So it would be 1. What if it was just 5? 5, because you're not passing it by choosing 5, right? So integers turn into themselves, so that's really nice. And usually it's the negatives that trip people up a little bit. What if it was negative 1.5 that was inside the bracket? Negative 2. Good job, Sophia. Because negative 1 is actually bigger than negative 1.5, right? Yeah, got to think number line style, okay? So if you struggle with that, literally think about a number line. Here's the number they gave you, negative 1.5. It's between negative 1 and negative 2. You cannot pass this number. You cannot get bigger. So all of this is not even an option, which means the integer you would have to choose is negative 2. Okay? All right, so do we get how that works? All right, so let's think about it. The integers produce themselves. So for this parent function, when I plug in 0, what would I get? 0. So 0, 0 is still like our vertex point, like it has been for many functions. What about when I plug in 0.5? 0. What about when I plug in 0.8? 0. What about when I plug in 0.9? 0.99? Okay, when is it going to stop equaling 0? When I get to 1. So what we do is this. Anything you plug in on the x-axis right here still equals 0, so it doesn't climb any in the y value. But when you get to 1, all of a sudden it makes a jump. When you plug in 1, what do you now get? 1. Up to here. Now, do we connect those? No, because nothing else gave us something between them. It just went from 0 to 1. So how we show that is that this little branch of the graph stopped at 1. Okay? Open circle because it's not actually hitting 1. Because at 1 instead, it jumped up here. Okay? Then when I plug in all the x values between 1 and 2, what do they all get rounded to? 1. So anything I plug in here is all 1, 1, 1, 1, 1 until I get to 2. Then this bar doesn't quite reach 2 and it jumps up here. So what is this graph going to end up looking like? Good, like a staircase, like steps. So they sometimes call this a step function. Okay? And it's basically, yes, going to look like stairs. Nope, just on the green door. Is that okay with everybody? All right, and so on your green door, we also want to include domain and range. So what would the domain of this function be? What are we allowed to plug in? Can you plug in something like pi? Yeah, what would it round it to? 3, okay? Basically, we can plug in any real number that we want, right? And do this rounding to it. So the domain is all real numbers. What about the range? Now, the steps do go on forever. It's kind of implied when you see a graph like this that they go on forever. So the steps go on forever. So there's no maximum and there's no minimum. But do you hit every number? Like, can you get a y value of 0.5? 0.5, there's no points at that y value, right? So how would we describe the range? Austin? Good, all integers. And in case you guys don't remember, I'm lazy, so I'm not going to write integers. Z was the symbol for the set of integers. Okay. And then just for, if you come across this step, oh, I know, highlighting doesn't really work on here, is like your main step. That's the step that everything kind of revolves around. And this point right here at 0, 0 is your vertex point. So if you stretch it horizontally, you actually change how long the steps are. Okay? And the steps never overlap, so the next step won't start till this one's ended. If you stretch it vertically, you change the distance between the steps. Okay? And then if you reflect it, you have to actually think about switching all the points over whichever axis you're switching it over. We'll do some more practice with that tomorrow, but I wanted you to see the parent function today. Okay? Yes, still.
What is it when you use the infinity signs to express the domain in notation?
Interval notation.
How would we do that?
So here you can't really do it for the integers. Okay? But for the all real numbers, we just go from negative infinity to infinity. All right. That's all we're going to do of that. Now you can go to your note guide if you printed it off. If you didn't print it off, you can make a choice of whether you want to get out a separate sheet of paper or if you still want to put the parent functions that we're going to go through on your green organizer. Okay? I posted a separate note guide for it, but it's just about graphing radical functions. That's all it would be called. All right, so first thing we want to find out is about the square root function and what it looks like. Okay? So we're basically saying what happens when we graph this. Okay? So somebody give me some points that you know exist on this graph. CJ. 4, 2. So he says when I plug in 4, I get 2, right? Sophia, what did you say? 0, 0. So I know 0, 0. I know 4, 2. What's another one in between there that I would know? Jarrett? Not 4, negative 2. When you plug in 4 here, you don't get negative 2. When you plug in 4, it's just what is the square root of 4, which is just positive 2. Because you aren't taking the square root of both sides of the equation. Quentin? Say it again. 9, 3. That's a little far from my graph, but yes, 9, 3 would work. Ghislaine? 1, 1. Good. These are usually the 3 main points I'm going to graph. It doesn't completely flatten out. It does keep growing up. It just grows really slow because remember, we're not going to reach 3 until we're all the way over at 9. When are we going to reach a height of 10? All the way over at 100. So it's growing slow. Okay, so I'm not drawing that to say it's completely flat, but I'm drawing that so I know it's not like shooting off. It's going real slow. Okay? So that's the basic parent function for a square root function. Which point do you think we consider like the vertex point, that everything is stretched or compressed away or towards on this graph? What's that? Which point? It's the same point we've used every single time. 0, 0. Yeah, the one that we've referred to as the vertex, and in some cases a little bit different, but yeah, this one right here. Okay, so everything will be stretched and compressed away from there. So you guys don't have to worry about the intercepts, but I mean, you should be able to find them. Remember, you find an x-intercept by plugging in 0 for y and a y-intercept by plugging in 0 for x. But domain. What's the domain of this function? Zeke?
X is greater than or equal to 0.
Good. Okay. Do you guys see why that is graphically? The graph does not exist on the left side of 0. That means for some reason we can't produce points when we plug in these x values. That makes sense with the function. Why doesn't the graph exist? Jarrett? Good. So if we tried to calculate the radical of a negative number, we would want to use imaginary numbers, but our graph is all based on real numbers, so we wouldn't see those points show up. So if you knew, like, oh, I can't plug in negative numbers, I can only plug in starting at 0, you would know this. Or once you saw the picture and the graph stopped here and didn't continue over there, then you would also know that, okay? And so this would be an interval notation from 0 to infinity. Okay. What about the range? The y values of the graph. Damien? I like the greater than part better. Greater than or equal to 0 because it's at 0 and then it's above 0. Okay, so the y values are all greater than or equal to 0. Why does that make sense with our function? How should we have known that we could not get y values smaller than 0 here? Austin? Good. Rad x, what's really in front of here, even though we don't see it, is like a positive symbol, right? There's no way we're going to get a negative value out of here. Okay, so we would be stuck here. So again, this would also be from 0 to infinity. All right, so one example of this, choose it wisely. Let's do this one. All right, so you look at it and you know that it's a square root function. So you're going to have the parent function memorized. The shape we just saw, you're going to want to know that's for a square root. Like you know for quadratic, 0, 0, 1 away, 1 up, 2 away, 4 up, right? We've got that memorized. Now for a square root function, we want to memorize 0, 0, 1, 1, 4, 2. If you don't have it memorized, if you know the parent function, you could quickly plug in and get it, okay? But we want to know that shape. Based on this equation, remember we want to factor out any horizontal stretches or compressions or reflections. So I want to factor out that -2 before I decide what transformations are happening. All right. So how is this graph going to be transformed from the parent function? What are our transformations? They work the same way they've always worked. We just have a new type of function. Soraya?
Horizontal translation of 2.
Good. Right or left?
Right.
Good. So the x minus 2 tells me a horizontal translation right 2. Okay. Yes. It is x minus 2, but remember the formula is x minus h, and that means the h value is positive 2, which is 2 to the right. So look on the back of your transformation thing, and it should review that. So remember, okay, no, so this is a different type of transformation. All right. So what else? Good, but horizontal. So the negative is inside of the function that we're multiplying by. So this is going to be a horizontal reflection. Actually, all of the transformation here are horizontal because all of the changes are taking place inside the radical. There's nothing happening beyond the radical. Okay? So we've accounted for this 2 by saying it shifts right. We've accounted for this negative with our horizontal reflection. What about the other 2? Jarrett? Okay, good. So remember, you can say horizontal because you see it on the inside. And then if you're unsure whether to say compression or stretch, think about what you're going to want to multiply by. And when it's inside of the function, we use the reciprocal. So we're not going to multiply everything by 2. Everything's going to get multiplied by 1/2. And that's why it's a compression and not a stretch. Okay? All right. Where should the vertex then be of our new graph compared to our parent function? So our parent function, the vertex is at 0, 0. Where is that going to get moved according to our transformations here? Good, 2, 0. It only depends on translations, right? Those are the only things that change the vertex. All the stretches and compressions change how the other things are around the vertex, okay? But they don't change the vertex itself. So our vertex will be at 2, 0. There's our shift to the right, 2. Okay? And so normally from here, 1 away would be 1 above, and 4 away would be 2 above. So this is how the graph would look if all we did was shift it to the right, 2. Okay? But what other transformation do we need to do? Jarrett? Good, we have to reflect it. Now, I shifted it first, so I have to be really careful about my reflection. It's horizontal, so it's from right to left. But does that mean this moves all the way over to -2? No, okay? The vertex point stays where it is once you've translated it. So that point's not moving. But where will this point now end up? Still over 1 and up 1, but over 1 in which direction? Left, because you are horizontally reflecting it. So you're moving it to the other side of the vertex point. Here. Okay? This point was 4 to the right and 2 above. I'm going to now redraw it 4 to the left and 2 above. Again, if you were good at these before, this is no different than what you were doing before. If you struggled with this last time we did it with the cubic, and the time before that with the quadratic, and the time before that with the absolute value, then now's another chance to learn it, but it's not going to go away. Okay? All right, so we've done this. We've done this. Okay, what about a compression of 1/2? What's that going to do to my points? Okay.
The 1 and 1 would go into a 1/2 and 1/2.
Okay, but not a 1/2 and 1/2, not both ways. What kind of compression is this? Horizontal, which means it's only adjusting the horizontal distance. So this point is still going to be 1 above, but instead of being 1 away horizontally, it's only going to be 1/2 away horizontally. So this point right here, instead of being 4 away horizontally, how far is it going to be? 2, because 4 times 1/2 is 2. Okay? And so there's my final graph of this function. So do you guys get we're doing the same things we've always done? Just new starting graph? Okay. All right, and then I'm just going to give you one more parent function. Oops. So the last parent function that I want you guys to add in there is the cubic, or the cube root, sorry. So it's like a square root. Can you plug negative values into a cube root and get a response? That's a real number. If you printed out the note guide, you can just print it and put it in the note guide. Can you plug in negative numbers into a cubic function and get a result? Yes. Okay. So let's plot some points. When I plug in 0, I get 0. That's my vertex point. Okay. What's another point someone can tell me? Jarrett. Not 2, 8. 8, 2. Right? So somewhere off at 8, it reaches up to 2. That's kind of off my graph, but 1, 2, 3, 4, 5, 6, 7, 8, 2. Okay. What's another point? Quentin. 1, 1. What about when I plug in -1? What do I get? -1. And when I plug in -8, I get -2. So this graph goes like this. Again, it is climbing, but it's climbing really slowly. That's why it kind of looks flat. Do you notice that it looks like the cubic just turned sideways? Like Anna pointed out to us, the inverse functions look like that. So what is the domain of this function? All real numbers. Good. There's no limitation, right? We can plug in positives, negatives, whatever we want. And what is the range of this function? Does it? Good. All real numbers. It doesn't skip anything. There's no maximum. There's no minimum. All real numbers. Which point do we consider like the vertex point on this graph? 0, 0. So when we translate, that point's going to end up in its new spot, and it's these other points that are around it that would get stretched, compressed, and reflected. Okay? But all the stretches, compressions, and reflections are nothing new. Does everybody understand that? You're doing them the same way that you did them before. Okay? So tonight's homework is actually from the note guide. So you guys can either bring it up at home. It's basically 8 problems. 4 of them are square root graphs, and 4 of them are cube root graphs. Okay? Does that make sense to everybody? Damien.
Still have a question for
Yep.
One, how did you get 0 to 0?
Because we shifted the graph to the right 2. So if you look at the parent function graph, you've got to start with the parent function. Its vertex was at 0, 0. So if you move that to the right 2, that point is now going to be at 2, 0. Because of the -2 in the parentheses with x.